Have you ever stopped to wonder why deserts are where they are? Or why a hurricane in the Atlantic spins differently than a cyclone in the Indian Ocean? Well, it all comes down to this massive, invisible engine that's constantly running on our planet, and it's powered by the sun. Today, we're going to pop the hood and see exactly how this global engine works. Everything, and I mean everything we're about to talk about, starts with this one simple fact. The sun just does not heat our planet evenly. You can think of it like an oven with some serious hot spots and cold spots. This one single imbalance is the spark that gets the whole engine going. So what is this atmospheric circulation anyway? Well, put simply, it's just nature's attempt to find some balance. The planet is always trying to move heat from where it's too hot, the equator, to where it's too cold, the poles. And it uses the air, the atmosphere, as its personal delivery system. To really get this, let's stick with that engine idea. Our atmosphere is literally a giant heat engine. And just like any engine, it needs fuel. For our planet, that fuel is the constant, massive temperature difference between the equator and the poles. And that engine has one job: move the heat. Think about it like this. If you shine a flashlight directly at a wall, you get a bright, intense circle of light. That's the equator. The sun's rays are hitting it head on. But at the poles, it's like shining that flashlight at a sharp angle. The light is spread out and weak. This creates a huge energy surplus at the equator and a massive deficit at the poles. And nature, it absolutely hates an imbalance like that. Okay, so to understand how this all works, let's do a little thought experiment. Let's simplify things. Imagine our Earth, but for a moment, let's pretend it doesn't spin. What would the air do then? On a planet with no spin, you'd get a super simple loop, just two basic steps. At the super hot equator, air warms up, gets less dense, and rises. Then, high up in the atmosphere, it would travel all the way to the poles, where it cools down, gets heavy, and sinks. It's a perfect convection cell, just on an epic planetary scale. And this is the why behind that simple loop. Over at the equator, you have hot air expanding, getting lighter, and rising. That creates low pressure at the surface. Meanwhile, at the poles, you've got the exact opposite. Cold, dense, heavy air is sinking, creating high pressure. And since air always flows from high to low pressure, boom, you've completed the loop. Now, that simple loop is a really neat idea, but of course, our planet isn't just a static ball sitting in space. It spins, and that spin adds a massive, game-changing twist to this whole story. And this right here gets straight to the point. That simple one-cell model we just talked about, well, it gets completely torn apart by the planet's rotation. The laws of physics just won't let that single, elegant loop exist on a spinning globe. So what is it? What exactly about that spin changes everything? How does a simple rotation turn that easy-to-understand loop into something so much more complex? The answer has a fancy name: the Coriolis effect. Now, it's not a real force pushing on anything. It's what we call an apparent force. As a parcel of air tries to move in a straight line, the Earth is literally rotating out from under it. So to us, standing on the ground, the air's path looks like it's curving. And here's the absolute key. The Coriolis effect doesn't create the wind, it just bends the wind. And the rules for this bending are actually super simple. In the northern hemisphere, it doesn't matter which way the wind is trying to go, north, south, east, or west, the Coriolis effect will always give it a nudge to the right. And you guessed it, in the southern hemisphere, it's the exact opposite: a constant, persistent deflection to the left. This relentless bending is precisely why that giant, simple one-cell model just can't hold up in the real world. Okay, so if the planet's spin breaks that one giant loop, what do we get instead? Well, the system settles into a new, more stable pattern, a three-cell system in each hemisphere. Let's break down the real picture. 3. That is the magic number. Instead of one huge conveyor belt of air running from the equator to the pole, what we actually get are 3 smaller, interlocking cells that work together to get that heat moved around. All right, first up, the powerhouse of the system, the Hadley cell. Air rises at the equator, starts moving toward the poles, but it gets deflected by the Coriolis effect and can't make it all the way. Instead, it cools and sinks around 30 degrees latitude. And here is the big aha moment. As air sinks, it dries out. This is exactly why the world's great deserts, the Sahara, the Arabian, the Australian outback, are all lined up right around this 30-degree mark. It is a direct consequence of the Hadley cell. Sitting in the middle, you've got the Ferrel cell. Now, this one's a little different. You can think of it like a gear that's being turned by the two cells on either side. At the surface, air tries to move toward the poles, but the Coriolis effect is really strong here, and it bends that wind sharply to the east. This creates the powerful westerlies, the winds that shape the weather for a huge portion of the planet, including most of North America and Europe. And finally, completing the puzzle, we have the polar cell. This one's actually pretty simple. It's driven by cold temperatures, just like our original thought experiment. You have super cold, really dense air sinking at the poles. It flows outwards along the surface until it meets warmer air from the Ferrel cell, right around 60 degrees latitude. That forces it to rise, and the loop is complete. So look, these three cells, they aren't just a diagram in a textbook. They create very real, very predictable wind patterns that wrap around our entire planet. And they don't work alone. They're actually part of a much bigger, interconnected system. So let's just quickly review the recipe for our global wind belts. You start with ingredient number 1, uneven heating from the sun. You mix in ingredient number 2, the basic physics of warm air rising and cold air sinking. And then you add the secret sauce, ingredient number 3, the planet's rotation. Put all that together and you get our amazing organized system of global winds. And this is where it gets even more incredible. Those steady winds, the trade winds, the westerlies, they're constantly pushing on the surface of the ocean, day in and day out. This action drives massive ocean currents, which are like giant rivers flowing within the sea. And these currents transport a truly staggering amount of extra heat around the globe. The atmosphere and the ocean are a true dynamic duo, working together to balance the planet's temperature. You know, if you only remember one single thing from all of this, let it be this right here. You don't have to memorize Hadley, Ferrel, and polar. Just get the core idea. Our entire weather and climate system is basically just a rotating sphere that is constantly trying to balance out uneven heating. Everything else, the winds, the deserts, the storms, it's all just a side effect of that one fundamental process. And that leaves us with a final and pretty critical question. This global engine has been running in a relatively stable state for a very long time. But now, as we continue to change the planet's energy balance by warming it up, how is this incredibly complex and vital system going to respond? That's a question scientists are racing to answer, and it's definitely something for all of us to think about.